Welcome back, everyone, to another deep dive. We've been looking at a lot of really cool stuff from the OEIS lately, and today we're going to dive into a sequence that's, right in that sweet spot where number theory meets this idea of partitioning integers.
Yeah,
So, we all remember breaking down numbers into sums back in the day, but today we're getting a little bit more specific.
absolutely. We're zeroing in on a sequence in the OEIS. It's A000174, and this sequence basically tells us how many ways we can write a non-negative integer as a sum of 5 squares.
5 squares.
Yeah,
Huh. So that's our constraint for today, 5 squares.
exactly, 5 squares. And it's fascinating how such a simple rule can lead to these really complex patterns and connections,
Yeah.
deep mathematical ideas.
Oh, okay. So let's get a feel for this sequence. Let's look at some of the first few terms.
Sure.
So for n equals 0, we have a 0 equals 1.
Right.
Which, makes sense because the only way to do that is 0 squared plus 0 squared plus 0 squared plus 0 squared plus 0 squared.
Yep.
And then for n equals 1, a of 1 is also 1.
Uh-huh.
Now, for those of you who are deep into number theory, that when we talk about these sums of squares, we usually care about the order and the sign of those square roots.
Absolutely.
So for 1, we're really looking at plus or minus 1 squared plus 0 squared plus 0 squared plus 0 squared plus 0 squared. And, we shuffle those plus or minus 1s around. But in this particular OEIS entry, it seems like those variations all get lumped together.
That's a good observation, and you're right, the OEIS entry itself doesn't explicitly state the convention for order and sign, but generally in number theory, when we work with sums of squares, we do consider those ordered tuples with signs, so we'd have plus or minus 1 squared plus 0 squared plus 0 squared plus 0 squared plus 0 squared and all its permutations.
Okay.
And while those represent different ordered sequences for this OEIS entry, they all seem to be counted as just one.
Gotcha. So we're kind of collapsing those variations down.
Yeah, exactly.
Okay. So moving on, for n equals 4, a of 4 is 2. So now we're talking about 2 squared plus a bunch of 0 squares, or 1 squared plus 1 squared plus 1 squared plus 1 squared plus 0 squared, and of course all the different arrangements and signs.
Yeah.
But again, those collapse to a count of 2 in this sequence.
Precisely. And you'll notice as n grows, the number of these representations, they generally tend to increase. I mean, you see the first few terms there, 1, 1, 1, 2, 2, 1, 1, 2, 2, and it keeps going, with some ups and downs, but the overall trend is upwards as n gets bigger.
Okay, so the further we go, the more of these representations we tend to find.
Exactly.
And while we're digging into these patterns, it's worth remembering what a fantastic tool the OEIS is. It's constantly evolving. It's driven by a passionate community, and it relies on the generosity of donors. So if you're a frequent visitor, consider giving back to the OEIS Foundation. It's what keeps this resource thriving.
I agree completely. The OEIS is truly a remarkable resource. And speaking of resources, what makes this particular sequence so interesting is its connection to other mathematical objects. The OEIS entry for A000074 actually gives us a formula A of n equals A002635 of n plus A025428 of n.
Okay, hold on a second. So we have a formula that connects the number of ways to represent n as a sum of 5 squares to 2 other sequences.
Yeah, that's right.
Okay, help me out here. What do these other sequences represent?
Well, that's the fascinating part. A002635 of n gives you the number of ways to represent n as a sum of 4 squares.
Okay.
So you see the connection, right? We're talking about 5 squares, and this other sequence is about 4 squares.
I see where you're going with this.
It hints at a relationship there. Maybe we could take a representation with 4 squares and just add a 0 square.
Ah, clever.
But then there's that second term, the A025428 of n, and that seems to be accounting for the representations that genuinely need that 5th square, the ones that can't be built from a 4-square sum by just tacking on a 0.
I see. So we have this base of 4 square representations, and then this extra term for the ones that are uniquely 5 square representations.
Precisely. And by exploring those other sequences, we can really gain some deeper insight into the structure of a 000174.
So it's like peeling back the layers.
Yeah, exactly.
Now, the OEIS entry also has a cross-refs section, which points us to equivalent sequences for 1, 2, 3, 6, 7, 8, 9, and 10 squares.
Right, and that's important for context. It shows us that our little exploration of 5 squares is actually part of a much bigger picture, this whole idea of representing integers as sums of squares. And you might start to wonder if there's some general formula out there for representing an integer as a sum of k-squares.
Yeah, I can see that.
And that's a really rich area of mathematical research. It's got a long history, and it's still an active area of study. So looking at these related sequences can help us see some of those underlying patterns and general principles.
It's like we're looking at one piece of a much larger puzzle. Now, for those of you who like to approach things from a different angle, the OEIS also mentions A295160.
Uh-huh.
This one's interesting because it gives you the largest number, k, such that A of k equals n. So instead of asking how many representations a number has as a sum of 5 squares, it's asking, given this many representations, what's the largest integer that has that count?
Right. It flips the question on its head.
It does. It's like an inverse problem.
Yeah, it is. And it raises some interesting questions about the distribution of these representation counts. For a specific number of representations, is there a limit to how big the integer can be? Are there patterns in how often certain counts appear?
So many questions. Okay, those of you who like to get your hands dirty with some computation, the OEIS provides a Mathematica code snippet. It's table powers representations 5, 5, to length, 0, 1, 100.
That's a really handy tool for exploring the sequence. If you know Mathematica, you can use this one line of code to generate the first 101 terms from n equals 0 to 100. That powers representations function, it figures out all the different ways an integer can be written as a sum of a certain number of powers, in this case 5 squares, and then length just counts them up.
Okay.
So it's a great way to do some empirical investigation. You can play around with it, form some conjectures about how the sequence behaves.
So if you're a student out there looking to really understand this stuff, running that code and seeing that sequence come to life can be a really powerful way to connect the theory to the computation.
Definitely.
Now, finally, for those of you who want to dive into the theoretical foundations, the OEIS entry mentions E. Grosswald's book, Representations of Integers as Sums of Squares, specifically page 84.
Ah, classic. That book is a cornerstone in this field, and the fact that they mention page 84 suggests there's probably some key theorems, proofs, or in-depth discussions related to this whole idea of representing integers as sums of 5 squared.
Sounds like essential reading.
It is. If you're serious about the theory, you need to check out Grosswald's book.
All right, so to wrap up our deep dive into OEIS A000174, we've seen how this sequence carefully counts all the ways a non-negative integer can be written as the sum of 5 squares, taking into account the order and sign of those square roots. We've explored its links to other OVIS sequences, like the one for sums of 4 squares, and we've highlighted some computational and theoretical resources you can use to go even deeper.
And stepping back for a moment, thinking about the wider field of number theory, these kinds of sequences, let us ask some fundamental questions about the structure of integers and the properties of quadratic forms. It's a field with a rich past, and there's still so much to discover.
Absolutely. All right, so here's a thought to leave you with. How do you think the number of partitions into k-squares changes as k increases? Are there any overarching rules or formulas that govern this behavior? And what kind of challenges might we face in trying to find those general results? Maybe you can use some of the resources and connections we talked about today as a starting point for your own exploration.
It's a great question to ponder.
It is. Thanks for joining us on this deep dive.
My pleasure.